Today, we're going to learn how computers communicate with one another. Almost everything we do online, sending emails, streaming Netflix, shopping, or even using Canvas, depends on a computer network. By the end of this lesson, you'll understand what a network is, how network devices communicate, what the major network devices do, and how cloud computing relies on networking. Don't worry about memorizing technical terms yet. Instead, try to understand how all of the pieces fit together. So take a moment to think about your home. How many devices connect to your Wi-Fi? Most people immediately think of their laptop and phone, but what about your TV, your gaming console, your smart speaker, your thermostat? Many homes now have 15 to 30 connected devices, and all of those devices form a network. So a computer network is simply a group of devices connected together so they can communicate and share resources. Notice I didn't say internet. A network doesn't have to include the internet. For example, computers in a classroom can share a printer even if the network goes down. So imagine if every computer had to work completely by itself. You couldn't print from your laptop, you couldn't share documents or watch Netflix or play online games. Networks make modern computing possible. Networks come in different sizes. A PAN, or personal area network, connects devices around one person. A LAN connects devices within one location, like your home or your school. A WAN, or a wide area network, connects networks across large geographical areas. The biggest WAN in the world is the internet. So here are some examples you probably recognize. Your Bluetooth earbuds connected to your phone, that's a PAN. Your home Wi-Fi, that's a LAN. And of course, the internet, that's a WAN. So let's follow what happens when you visit a website like weather.com. You type in the domain name in your browser and you press enter. Your computer sends a request asking for the website. The web request goes to your router. The router forwards it across the internet, and the weather.com server receives the request, then sends that information back. And all of this is happening in a fraction of a second. So you could summarize it in just 5 steps. Your computer sends a request, the router forwards the request, the internet carries the request, a server processes the request, and then a response returns to your computer. So we just talked about how data moves from one computer to another. The OSI model helps us understand the different steps involved in that communication. OSI stands for Open Systems Interconnect. The OSI model doesn't represent physical hardware. It's just a conceptual model that helps us understand the communication process between two computers. Rather than thinking of a network communication as one large task, the OSI model breaks it into 7 smaller layers, where each layer has a specific responsibility and works with the layers above it and below it. For example, when you send an email or load a web page, the data passes through all 7 layers before it leaves your computer. And when it reaches the destination, the process happens in reverse as the data moves back up through the layers. You don't need to memorize every detail of every layer. The important idea is that network communication is organized into layers, with each layer performing a specific job. This layered approach makes networking easier to understand, to design, and to troubleshoot. As we continue through this lesson, you'll see that many of the networking devices that we'll discuss perform their work at a specific layer of the OSI model. So next, we're going to meet the devices that make networks work, and each one has a different job. So every device that connects to a network has a network interface card, or NIC. Think of the NIC as the device's network connection. Without it, a computer wouldn't be able to communicate with any other devices. Now, a NIC allows a device to connect to a network. It can be built into a computer, which is the most common, or it can be added later as a USB Wi-Fi adapter or an expansion card. So a NIC can provide either a wired Ethernet connection or a wireless Wi-Fi connection, depending upon the type of network interface that's installed. And most computers already have a built-in NIC. If a computer doesn't have the type of network connection it needs, an additional network adapter like a USB Wi-Fi adapter can be added. Most laptops include both a wired Ethernet NIC and a wireless NIC for Wi-Fi connections. So when you connect your laptop to your home Wi-Fi or plug in an Ethernet cable into a desktop computer, you're using the NIC to send and receive data. So the next device, a modem. This is the device that connects a home or a business to an internet service provider or ISP. Without a modem, your network would still work internally, but it wouldn't be able to communicate with the internet. Think of the modem as the front door between your network and your internet provider. The modem receives the internet connection from the ISP and passes it to the router. Now, most homes only need one modem because there's usually only one internet connection entering a building. The router is often called the traffic cop or the traffic director of the network. Its job is to decide where information should go. Imagine several people in the house are online at the same time. One person is streaming Netflix, somebody else is playing an online game, somebody else is checking email. All of that information arrives through the router. The router makes sure the Netflix data goes to the TV, the game data goes to the gaming computer, and the email goes to the correct laptop. The router also connects your local network to the internet. Without a router, devices inside of the building wouldn't know how to reach websites or other networks. Now, many people confuse modems with routers because internet providers often supply a single box that contains both devices. So even if they're combined into one piece of equipment, the modem and the router are still performing different jobs. The next device is a switch. This connects multiple wired devices in the same network. So unlike a router, a switch doesn't connect your network to the internet. Instead, it allows computers, printers, and other wired devices to communicate efficiently with one another. Imagine a business with 20 desktop computers. Rather than connecting each computer directly to the router, they are connected to a switch. Then the switch manages communication between all of those devices and forwards the information only to the device that needs it. Large organizations often have many switches because they have many wired devices spread throughout a building. Whenever you need to connect many desktop computers using Ethernet cables, you'll probably need one or more switches. The next device is a wireless access point. This allows wireless devices to connect to a network using Wi-Fi. Think of it as the device that broadcasts the wireless signal. Now, laptops, smartphones, tablets, and all other wireless devices connect to an access point instead of plugging them into an Ethernet cable. The access point is connected to the network using a cable, usually a switch, and then it provides a wireless access for nearby devices. Many home routers include a built-in wireless access point, but large schools and hospitals and businesses usually have many access points because one access point can't provide strong enough Wi-Fi coverage for an entire campus. So let's compare these devices one last time before we see them working together to complete a network. Notice that each device has a specific job. The network interface card allows an individual device to connect to a network. The modem brings the internet connection into the building from an ISP. The router directs traffic between the local network and the internet. The switch connects multiple wired devices so they can communicate effectively. And then the wireless access point provides Wi-Fi So laptops and smartphones can join the network. None of these devices perform exactly the same function. They work together to create a complete network. So now let's look at a real example and identify where each device fits. So this is an example of a small medical clinic. If we start at the top, the internet enters the building through the modem. The modem connects to the router, which acts like the traffic director. The router connects to a switch, which allows multiple wired devices to communicate on a network. Now, the desktop computers and the printers are connected directly to a switch using Ethernet cables. But then there's also a wireless access point connected to the switch, and it provides Wi-Fi. So the laptops and the tablets and the smartphones can join wirelessly. So every device has a path back to the router and ultimately to the internet. So as you examine this network diagram, ask yourself, where does the internet enter the network? Which device directs network traffic? How are the wired devices connected? And how are the wireless devices connected? And then how do all of the different devices communicate with one another? So when a server sends information back, it needs to know exactly where to send it. That's why every device on a network has an IP address, Internet Protocol address. Just like every house has a mailing address, every device connected to the internet has an IP address. And without that address, other computers wouldn't know where to send information. If you don't know grandma's address, you cannot send her a birthday card. So IP version 4 has been around for decades. As more devices connected to the internet, we began running out of addresses. So IP version 6 are much longer than IP version 4 addresses because they provide an enormous number of unique addresses for today's billions of internet connected devices. A standard IP version 6 address is written as 8 groups of 4 hexadecimal digits separated by a colon. You can see that there is a compressed form of that, but these two hexadecimal addresses represent the same thing. The second version is simply a shorter way of writing it. And you don't need to memorize the format, just know why IPv6 exists. So what about cloud computing? Cloud computing means just using software or services that run on computers somewhere else instead of on your own computer. Things like Google Docs, Microsoft 365, and Canva. The software runs in the cloud. You simply access it over the internet. And cloud storage is a slightly different thing. Instead of storing files on your own computer, they're stored on remote servers. Examples of this include Google Drive, OneDrive, Dropbox, and Box, which is a free Weber cloud storage that you get as a student, and iCloud. Because they're online, you can access them from almost anywhere. And there are a lot of advantages to cloud services. You can access files from anywhere. You can collaborate with other people. Your files are backed up. You don't have to carry around a jump drive, or you don't have to burn things to a CD. But there are some trade-offs. First, you need internet access. There could be some privacy concerns, and some services actually require a subscription. So let's trace one final example. You save a document to Google Drive. Your laptop sends the file over the Wi-Fi. Your router sends it through the internet, and then Google servers store the file in cloud storage. Later, when you open that Google Drive on your phone, you're viewing the same file from the Google servers. So everything we've discussed today works together to make that possible. So in summary, we learned what computer networks are. the different types of networks, the devices that make networking possible, why IP addresses are important, and how cloud computing and cloud storage depend on networks. In the next lesson, we'll shift our focus from how networks work to how we protect them as we begin our study of cybersecurity.